This meeting is being recorded.
Welcome everyone to session 10. Today we're going to talk about something that most people ignore until it is too late, which is evaluating technical efficiency and performance. So, up to this point, we have, let's go, yes. Up to this point in this course, we have been mostly focused on what the chatbot says. We talked about the logic, is it reasoning correctly? We talked about fairness, is it treating users fairly and not being biased. We talked about security and transparency. Is it safe? And does the user understand what is going on? So, all of that was about its brain and the ethics. Today, we care about something much more brutal, which are speed and efficiency. So in this session, we are shifting from what does the chatbot say to how fast, how reliable, how cheaply can it say it. Because performance is not just a nerdy back end topic, it directly hits three things everyone cares about, which are satisfaction, user satisfaction, scalability, and also cost. So think about it from a user perspective. You don't care if the model is GPT something or Magic Unicorn AI or whatever. If you are staring at loading spinner for 12 seconds, you are gone. You close the tab, you complain to the group chat, and never come back. So, from a business side, if your bot crashes or slows down the moment 500 users show up at the same time, that is a failure. So, it might have the smartest answers in the world, but if it dies under load, it is not a product, it's a demo. So, and then there's cost. If every conversation costs so much that finance starts asking, why are we paying more for this chatbot than for three human agents? You also have a problem over here. So, the rule for today is very simple. A chatbot that responds slowly or crashes under high load is a failed chatbot, no matter how intelligent it is. Performance is part of the definition of quality, not an extra feature. Okay, so let's go on for the next slide. No, I'm here. So yeah, so now that we agreed performance matters, let us give it a proper structure. There are three main things that we care about when we talk about technical efficiency. They are latency, throughput, and resource consumption, and and then how we actually measure all of that using percentiles like P50, P95, or even P99. We will talk about these ones later in the course. Let us start with latency. Latency is simply how long it takes the system to handle a single request from the moment the user hits enter until the chatbot's reply is ready. Um, this is latency. In human terms, it is like ordering coffee. You say one latte, please. Latency is the time from the moment you ask the waiter until the cup is in your hand. So if that takes 20 seconds, that's fine. But if it takes 5 minutes, you start judging your life choices. Latency for a chatbot is made of several pieces, which are first, network latency. This is the time it takes for the request to travel from the user's device to the server and for the response to travel back. If your user is on a bad mobile network or on the other side of the world from your server, this part grows. It is basically the internet distance. Second, we have processing time. This is server side coordination. Things like checking authentication, routing the request to the right service, logging, calling other APIs. It does the part where gluing everything together. Sometimes the AI model is fast, but this part is messy and you lose time in your own backend. Um, Third, which is model inference time. This is the AI model itself, thinking and generating the answer. How long it takes the model to go from prompt to tokens. If you pick a huge model or you run it on a weak machine, this part gets slow. Fourth, which is knowledge base query time. If your chatbot needs to search a database or do a vector search over documents, that query time is included in the latency. So if your database is slow, your chatbot is slow, even if the model is fine. So all of those pieces add up. Users do not care which part is slow. They only see the total latency. Now, the second concept is throughput. Throughput is how many requests your system can handle per second. You will often see this written as RPS, which is request per second. So if we said latency is how long does it take to serve one person a coffee, throughput is how many or how many coffees can we serve per minute before the bar collapse. There is an inverse relationship here. As you push more users through the system gets busier. Queues starts forming, and latency usually increases. So more throughput often means more delay. If you push beyond what the system can comfortably handle, the key thing here that we want to know is what is the maximum throughput the system can handle before latency becomes unacceptable. So, for example, maybe it is fine up to 200 requests per second, and after that, response time jumps from 2 seconds to 12 seconds. That is the cliff that you want to know, that you want to know about before real users find it. Okay, so third, we've got resource consumption. This is where we monitor CPU and memory and GPU usage. We want to see how much the system is eating while it is working. This helps us spot a few ugly things, which like memory leaks, where memory usage keeps growing and never goes back down, inefficiencies where the system is using far too much CPU or GPU for what it is doing, or unstable behavior, like the system works at the start of the test, and then after 10 minutes at high load, it collapses or slows down. So if all your CPUs are at 100% and memory is almost full, you know that you know why your latency is exploding. Now, all of this is nice, but how do we quantify it? This is where evaluation metrics comes in, especially percentiles. Instead of only looking at averages, like which can be very misleading, we use P50, P95, and P99. So P50, or the median, is the typical case. Half of your requests are faster than that value, half are slower. This tells you what a normal experience looks like. P95 means 95% of requests are faster than that number, and 5% are slower. This is closer to what do most users actually experience when things are a bit busy. And P99 is the extreme tail, the slowest 1% of responses. This often represents the painful edge cases. like users on bad networks or when your system is under stress. This P99 measure this. So why does this matter? Because an average can lie to you. So imagine you have four responses that took 1 second and one response that took 20 seconds. The average here is 4.8 seconds. You might think not great, not terrible. But for 80% of users, it was actually 1 second. So but for one user, it was a disaster. It was a whole 20 seconds. So we look at percentiles to see the whole picture. Our goal is usually to minimize P95 and P99. We want the worst cases to still be acceptable, but not embarrassing. So this theoretical framework, latency, throughput, and resource consumption and percentiles, like P90, P50, P95, and P99, is how we talk about technical efficiency in a serious way. Instead of saying it feels fast on my laptop, we measure it. Okay, let's move on. Okay. So let's talk about a situation that happens constantly in real life with any complex system, which is the system is slow. The question we always ask ourselves is the same, but it's crucial. Where exactly is the problem? Is the delay coming from the model, the database, the network, or even our own code? This is where the entire process of diagnosing and fixing performance issues comes in. So we will look at two big ideas here: profiling and then optimization. Okay, so profiling techniques here. So this is just a fancy professional word for the simple concept, which is measure where the time actually goes instead of guessing. So you have to move past gut feelings and rely on hard data. How do we do this? So we use specialized tools like that break down a single user request. Let's say from the moment the button is clicked until the response is sent, we measure each process into tiny pieces. So tools like Open Telemetry and language specific profilers, which are in Java, in Python, it's like C profile, and in Java is like JFR. So we look inside a single process. These tools produce a breakdown, often called flame graph or a trace, that literally shows you this function call took 10 milliseconds, or this database query took 200, or the model prediction took 1.5 seconds. So each one of these processes are um, i- cut down into pieces and studied each time for for each one of these. So, let's talk about the signal and the noise. For example, imagine you run your profiling tool and it clearly shows that 80% of the total request time is spent inside the function called model.predict. That is your clear signal that the AI model is undeniably the bottleneck here. So if you ignore that data and start optimizing your SQL queries, you are essentially rearranging chairs while the engine is on fire. So the biggest mistake many teams make is that they optimize what feels slow or what they personally understand better, and instead of what the data shows is actually slow, or profiling forces that to face reality. Okay, so let's go on to the optimization strategies. Here, once we profiled and know exactly where the bottleneck is, we don't just throw random tricks at the system. We must match the strategy to the specific problem. Okay, so if a model is slow, as we said before, the model predict function is the slow part. We need to focus on making the computation faster. So we have a few powerful options over here, which are model distillation or quantization or better hardware, software, or even infrastructure. So a real life example here: if a friend complains that it takes 30 minutes to get to work and you discover that they are walking, the optimization here is not to buy lighter shoes. The solution here is to change the infrastructure itself, to use a bike or a scooter or a car. Same logic, to use the right infrastructure for the heavy lifting things in building a chatbot. Okay, so let me give you an example. Let's say a database is slow. The SQL queries are the bottleneck over here. So this is a completely different story. We look at two main areas here, which are indexing and caching. So if if your user profile data never changes more than once a day, and your chatbot queries I'm sorry, and the chatbot queries it on every single message, you can cache that data for an hour. Why pay the heavy database cost every single time? The cache result can be returned in milliseconds. So the key takeaway here is simple. Do not guess. Just profile to see where the time is actually going, then use the right optimization strategy for that specific bottleneck. So, yeah, let's move on for the next slide. Okay, now that we know how to diagnose performance problems, let us talk about how to actually test the system in a serious way. So there are three main kinds of performance tests that you will see a lot, which are load testing, stress testing, and soak testing. You can think of them as normal life, crisis, and long-term relationship. So first, load testing. Load testing is about simulating normal or expected usage. For example, you might say we expect around 1,000 concurrent users at peak time. You simulate that. You send traffic to your chatbot as if 1,000 users, real users, are using it at once. And you watch what happens then. The goal here is to see if the system behaves correctly under the expected load. Does the latency stay within the target? For example, P99 latency less than 500 milliseconds. So even the slowest 1% of requests are still under half a second. And what about the error rate? Maybe your SLA says error rate should be below 0.1%. If during load testing you see P99 jump to 3 seconds or the error rate goes up to 2%, that means the system is not ready or not fully ready for the real world, even if it looks fine with just 10 test users. Um, so load testing is basically can it handle what we expect in real life without embarrassing us. Second, which is stress testing. So, stress testing is more evil and actually more fun. Here, you say, let us push this system beyond its limits and see when and how it breaks. You keep increasing the number of requests or the traffic rate past the safe zone. You go from 1,000 users to 2,000, then 5, then even more until the system starts to struggle. So what you care about here in this step is not just the breaking point, but how the system fails. Does it degrade gracefully? For example, responses slowly get a bit slower. Maybe some non-critical features get disabled, but the core functionality is still works, or does it crash completely? So everything goes red. The service dies. Users get error everywhere, and someone is screaming on Slack. So you also want to see what happens after the stress when you stop the overload and go back to normal traffic. Does the system recover automatically, or does it stay in a bad state until someone restarts things again manually? So, good systems fail in a controlled and predictable way. Bad systems panic and collapse. So, third, we've got soak testing, also called endurance testing. Soak testing is about time, not just intensity. Here, you run the system under a moderate but realistic load for a long period, hours or even days. Why? Because some problems only appear slowly, like memory leaks, where memory usage keeps creeping out little by little, or gradual slowdowns. um everything looks fine at the start, but after 6 hours or 24 hours the system becomes slower and slower. In a quick 10-minute test everything might look perfect. In a 24-hour soak test you suddenly see that latency keeps increasing over time, or that one service eventually crashes every night. So soak testing answers the question, can the system survive in production for long periods and not just survive for a short benchmark? Okay, so 1 second, please. Okay, so let's go for the next slide. Okay, so This this is a critical and crucial topic that directly follows performance testing, which is scalability. We've diagnosed the bottleneck, which are profiling, and we've tested the limits, the load, the stress, the soak testing, and now we are to talk about the final and critical step, which is scalability. So, scalability is the ability of your system. Um, let's say it's a chatbot or a website or even a complex API or whatever. We scale or we test how it handle a growing amount of work gracefully. If your traffic doubles, your system shouldn't just crash; it should be able to handle that growth, ideally without a significant loss in speed or whatever. So there are two primary ways that we achieve this in the real world: the vertical scaling and the horizontal scaling. So the vertical scaling, which is scaling up, is the simplest, most intuitive approach. It means that you take the existing server or machine that you're running your application on and you add more resource to it. So how it works, maybe you upload or like upgrade the RAM, which is the memory of your chatbot or of your server, a faster CPU, which means more cores, or a bigger, faster SSD, which is storage. So think of it like running a race car. You're taking one vehicle and making it as powerful as possible. So the pros here are it's simple and it's fast to implement. It requires minimal changes to application code. It's often just a few clicks in a cloud console or a phone call to a data center, and done. But the cons here that it's limited. There is an inevitable limit to how big that you can make a single machine. You can just buy a server with $10,000 cores. Also, a single point of failure, if that single super powerful server goes down, your entire application is offline. There are there is no redundancy over here. So when do we use this? When do we use the vertical scaling? It's for simple internal services or for a database that is hard to cluster, but it is really rarely the final solution for an application. Let's talk about the horizontal scaling, which is scaling out. This one is the standard for high load applications like chatbots and large web services. This is about adding more servers or virtual machines or container or whatever you can call it. We add more to the environment and distributing the workload across all of them. The how it work? We could clone the application and put them behind a load balancer, and the load balancer directs incoming user traffic to the least busy server. Instead of one race car here, you have a fleet of identical standard cars working together. If one breaks, the other instantly pick up the slack. So the pros here are that high availability. If a server fails, the load balancer stops sending traffic, and the users immediately are redirected to server B, server C, the other servers. Also, the near infinite capacity. You can theoretically keep adding servers indefinitely to handle almost any load. But the cons are that it requires code changes. Your application must be stateless. The request must be handled by any server, not just the one that saw the user's previous request. Operational overhead. Managing dozens of hundreds of servers is much more complex than managing just one. So, um, the ultimate goal here is linear scalability. The real test of a successful horizontal scaling strategy is achieving linear one. The definition of this step, which is the goal, to double the number of servers, it should roughly double the system's throughput, which are requests per second, without significantly increasing the response latency. So, imagine you have a chatbot that is running on two servers. It handles 1,000 requests per second with a P95 latency or of a 200 millisecond. So you decide to scale up for a holiday season. So you double the capacity by adding two more servers, bringing the total to four servers. Expected linear scalability here. The result here is 2,000 requests per second at roughly 200 millisecond latency. The actual problematic result is that the throughput only increases 1,200 requests per second, and the latency suddenly jumps to 500 milliseconds. So, what happened here? This is a classic failure of linear scalability. Adding hardware did not help because the bottleneck was likely not the server compute, but a shared resource they all depend on. So the four application servers are all fighting for limited connection or resource on the single unscaled database server. The database became the new bottleneck over here. So, how to fix this? We need to scale the bottleneck. We should add more database replicas, which is horizontal scaling for reads, or maybe employ caches to take the pressure of the database. So, Linear scalability proves that you have identified and scaled all the key components of your architecture, not just the web servers. So, this is the hallmark of a system ready for massive, unpredictable traffic growth. Okay, so let's move on. So, let's wrap things up. In this session, we have covered the critical journey from a working demo to a production ready system. The simple truth is that technical efficiency is as vital as the AI's intelligence. A brilliant chatbot that takes 5 seconds to reply is, in the eye of the user, a broken chatbot. Real world users will not wait. Um, by rigorously evaluating these three pillars, you ensure your system is fit for the market. Latency, you must focus on the user's experience here, especially the P99 latency, to ensure responses are fast and feel instant, even for the slowest 1% of users. Also, the throughput, you need the raw capacity to handle the volume, ensuring your system can process thousands of requests per second during peak hours, of course. And finally, is the scalability. You have built your systems for growth, favoring horizontal scaling to guarantee that when the user base doubles, your infrastructure can double its capacity linearly. So, the big picture, why we do all this. The outcome of this performance is transforming a concept into a reliable and stable and scalable piece of engineering. You have moved past three functionality and ensured reliability, stability, and customer confidence. Um, Reliability is that the system won't crash during sudden traffic. Scalability is that the system does not slow down or leak memory over period of time. And customer confidence, which is the service level of objectives, um, our SLOs for spread and uptime can actually be met. Okay, so what are we having for the next step? Um, Making the system fast and stable is only half the battle. We now transition to the final and most exciting step, which is assessing the chatbot's continuous learning ability. A static chatbot gets outdated quickly. The real power of an AI lies in its capacity to grow smarter with every single interaction. In our next session, we will explore how to harvest user failures like fallback rate and missed intents as valuable training data, the closed loop feedback system necessary to retrain the model and redeploy it without any downtime. Also, the metrics that prove the model is actually getting more accurate over time, leading to a higher resolution rate. Okay, so this is the next phase where we turn data from production into intelligence, ensuring that chatbot does not just work fast, but that it learns and evolves and provides increasing value to the business. Thank you so much for listening. I will close this meeting right now.